Hello everyone, I'm Norman Wildberger. We're here at the University of New South Wales. And today we're going to talk about algebraic number theory, which is a 19th century development that really prominently uses this theory of rings. That's sort of where the theory of rings comes in. So we've been talking about some algebraic objects in our last couple of videos. We talked about groups in the context of Galois theory, and fields, also in the context of Galois theory, really. So groups, for example, the symmetric group Sn, and fields, for example, the rational numbers, or Q, are sort of prominent examples of those kinds of objects. And today we want to focus on a sort of a third important kind of object called a ring. And so the theory of rings came out from algebraic number theory, and we want to talk about that story a little bit. So I'm going to talk about rings, but I probably have to say a little bit about some notation. So I'm not a big believer in infinite sets. So I don't believe in infinite sets. That may seem like a strange kind of admission as for a mathematician, because infinite sets are used all the time in mathematics currently, all right? But in previous centuries, they didn't. And if we go back historically to Gauss and to Euler and to even many 19th century mathematicians, they didn't quite have the same confidence in this concept as we do today. So because I want to talk about the 19th century mathematics, but I also want to say things which aren't really in contradiction to my own internal beliefs, I'm going to use slightly different notation and different concepts sometimes. So instead of the set of rational numbers, I prefer to rather think about the property of a number being a rational number. So for me, a rational number is an expression of the form a over b, where a and b are integers. Okay, so integers is sort of my way of trying to get at the set of integers without having to say that there's an infinite set, actually, just in terms of properties. Okay, and I also have to confess, and this will become quite important in this lecture, that also I am skeptical, let's say, about infinite processes and creating algebraic structures from infinite processes without a prior theory of infinite processes. In particular, about the real numbers and the associated complex numbers. So this is a key point. So a key point is that the fundamental theorem of algebra, which we've talked about, which was a favorite result of Gauss, the fact that every polynomial supposedly has zeros in the complex plane, is to me a rather suspect statement, and it's only approximately true. So if we want to do things completely accurately and completely logically, we have to replace the usual statement of the fundamental theorem of algebra with an appropriate approximate statements involving rational numbers and complex rational numbers. But I don't want to do that. But nevertheless, it's going to be important for this talk because the complex numbers and the fundamental theorem of algebra are kind of an elephant in the room when it comes to algebraic number theory. And we're going to see that okay, this definitely has something to do with this story. All right, so let's put that aside now, however, and talk a little bit about just an introduction to rings. Okay, what is a ring? Well, it's a generalization of the integers. Okay, so that's usually denoted z, or in my notation, the property of being an integer. And we're talking about 0, 1, 2, 3, and so on, and also -1, -2, and so on. Okay, so what are the main operations here? So the main operations are addition and multiplication. And the special numbers are 0 and 1. Okay? So 0 is an additive identity, and 1 is a multiplicative identity. And we have in addition, we have the ability to take additive inverses. So we have that n plus minus n equals 0. So we can also write n plus minus n as n minus n if we like. So we have subtraction, i.e. Additive inverses and subtraction. All right, I don't want to give the entire definition of a ring, and there will be quite a lot of other definitions here that I'm not going to give precisely because I just want to give you an overview. So we're going to concentrate on the integers as being an example of the ring, sort of the fundamental example. And prominently, what we don't have in the integers is division. Okay? Well, that's only selectively true. We have some selective amount of division, but we don't have general division. Okay? But we do have some notion of divisibility. There is a partial notion, let's say, of dividing. Namely, we say that A divides B means that you can write B as A times C for some C. All right, so for example, 3 divides 6, or -5 divides 25. And then once we have this divisibility, then of course we have prime numbers. So a prime number P has the property that if P divides a product A times B, then P divides A or P divides B. So that's a kind of fundamental property that defines prime numbers. And we are we have to be a little bit careful because we, sort of by convention, we have to worry about negative numbers playing the same kind of role. So there's another condition that we want the primes to be. We want primes to be a positive. So primes are 2, 3, 5, 7, and so on. And in addition, we have the notion of a unit. The units are just plus and minus 1. So these are the numbers which divide 1. Or we could also say, or they are the numbers with multiplicative inverses. It's another way of saying what a unit is. And then the fundamental theorem of arithmetic, going back to the ancient Greeks, we can state it now in terms of integers as every n, which is an integer, can be written is a product of primes up to possibly a unit. In essentially one way. So for example, 12, for example, is 2 times 2 times 3. Well, say minus 18 is minus 1 times 2 times 3 times 3. All right, so every number can be written as a product of primes in essentially one way. That means we can permute them, but we can't really change the primes that are involved in the composition. And possibly we need to throw in a unit minus 1 in order to account for negative numbers as well as positive numbers. All right, so these are sort of fundamental properties of the integers that when people wanted to generalize the idea of integers, they looked to these properties as being sort of natural things to look for analogs of. And there is a very nice generalization of a ring, a very important one, which is sort of the second important example of a ring, and that's polynomials over a field. Or let's say polynomials over Q. Or rat. So we're talking about just polynomials in one variable. So polynomials of the form p of x equals something like 3 minus 2x plus 1/2 x cubed, something like that. Polynomial with coefficients in the rational numbers. That's the kind of object that we have. And we can have operations of addition, subtraction, and multiplication, just as before. Basic operations. In some sense, high school arithmetic is really all about extending the arithmetic from integers and rational numbers to polynomials. So the arithmetic of polynomials is really sort of what we call high school algebra. All right, so we have these basic operations, and we also have a notion of divisibility, or the idea of factors of a polynomial. And in fact, there is unique factorization. Just as there is for integers. So every polynomial is a product of, well, we usually say irreducible polynomials instead of prime polynomials. And these are the polynomials that cannot be factored further, and up to units. And let me give you an example that will be interesting. So for example, well, let's do first a simple example. X cubed minus 1, for example, factors as x minus 1 times x squared plus x plus 1. Okay, and those are both irreducible factors in the sense that you cannot further subdivide them into products of smaller degree things. Here's a more fancy one, x to the 15 minus 1. All right, that turns out to be x minus 1 times x squared plus x plus 1, the same factors that are appearing here. And then x to the 4th plus x cubed plus x squared plus x plus 1. And then there's a more interesting polynomial, x to the 8th minus x to the 7 plus x to the 5 minus x to the 4 plus x cubed minus x plus 1. It's a factorization of x to the 15 minus 1. In fact, it turns out that these polynomials that are constituents of this kind of expression when you have x to the n minus 1, these are quite important polynomials called cyclotomic polynomials. And in fact, there's sort of 1 associated to each one of the divisors of 15. So this one's sort of associated to the divisor 1. This one's associated to the divisor 3. This one's associated to the divisor 5. And this one's associated to the divisor of the number itself, 15. All right, so this is a sort of a key idea that a lot of the arithmetic that's valid for integers is also valid for polynomials. And they share, these two domains share a lot of properties. In particular, they share the idea of a prime or irreducible, the idea of unique factorization, which is really a key point in arithmetic, to be able to factor a number or polynomial uniquely. All right, so now we come to 19th century work, which only slowly eventually realized that there was this notion around, but eventually investigated it in quite a rich fashion. And there are quite a few names associated with this. So in the 19th century, other rings appeared, obtained from the field extensions that had their work in the Galois theory kind of questions that we talked about last time. And so these are called rings of algebraic integers. And they were studied by many prominent people, Gauss, Dirichlet, Kummer, Eisenstein, Hermite, Kronecker, Dedekind, and others. So let me try to explain what these kinds of field extensions are. So the usual story that the 19th century mathematicians would have thought about is in terms of the complex numbers, okay, and the fundamental theorem. And they would have taken a polynomial, and I'm going to take the polynomial that appeared over there. So let's introduce, let's say f of x happens to be this cyclotomic polynomial, x to the 8 minus x to the 7th plus x to the 5 minus x to the 4 plus x cubed minus x plus 1. That's one of the factors of x to the 15 minus 1. And this is a very special polynomial because it's a factor of x to the 15 minus 1. And so if we want to know what its zeros are, it's just a question in terms of the geometry of the complex plane, in terms of talking about 15th roots of 1. Okay, we're really solving the equation x to the 15 minus 1 equals 0, and these are some of those roots. So let me try to give you the standard picture of this. All right? So the standard picture is that we've got basically 15th roots of 1, and they form, well, first of all, let's just look at the pentagon, the 5th roots of 1. Okay, so This would be in the standard notation e to the I 2 pi on 5. And if we divide this angle by 3, if we subdivide, trisect this angle, assuming we can do this, we're at least sort of geometrically doing it, then we obtain, for example, this point here would be e to the I 2 pi on 15. And let's call that xi. It's supposed to be a Greek number, Greek letter there. All right. And then in terms of that xi, the other ones are all powers of xi, going all the way around till its complex conjugate here would be xi to the 14, and 1 is xi to the 0, or xi to the 15. All right, so these are the 15th roots of unity. And that means that they are exactly the zeros of this polynomial x to the 15 minus 1. And in particular, 8 of them are going to be the zeros of this one, which is a factor of that. Now, this cyclotomic polynomial, its zeros are a very special subset of these 15. The zeros of this one are, well, first of all, xi, and then also xi squared, and xi to the 4th, and xi to the 7, xi to the 8, and xi to the 11, and xi to the 13, and xi to the 14. 1, 2, 3, 4, 5, 6, 7, 8 of them. And what's special about those particular powers? Well, those are all the powers, okay, that are relatively prime to 15. Exactly the ones that are relatively prime to 15. In other words, that they're not nth roots of unity for some smaller n. This one here is not in this list because this one is actually an nth root of 1 where n is 5. Okay, it's still a factor of x to the 15 minus 1, but it's not a kind of a primitive 1. Okay, so there are a lot of problems with this story logically. Okay, and a lot of these problems are known historically because some of them go back to the ancient Greeks. One of the problems is that if you have a general angle and you ask, how am I going to trisect that angle? That is a very hard problem. Of course, you can do it approximately, but actually being able to exactly trisect that angle is, well, not possible by the Greek methods, suggesting that there's something difficult about getting at a point like this arithmetically, even if we assume we've already got this one. Okay, so if I go to my calculator, my computer, and I can ask it to calculate this 15th root of 1, I can ask Maple or MATLAB or something like that to solve this equation, then I can find that this thing equals, well, it depends on how many decimals I ask it for, but suppose I ask it for 5 decimals. It will tell me that it's 0.91355 plus 0.40674i. Of course, that's just an approximation. And if I actually then ask, well, what is then c to the 15? If I take this value and I raise it to the 15th power, my computer will spit out that that's actually equal to 1.0001 plus 1.8289 times 10 to the minus 5 times I. In other words, I'm not actually getting 1. I'm getting a number that's reasonably close to 1. And that's, of course, because this is only an approximation. But the point is that it's impossible to actually spit out the entire number so that the identity is exactly equal, unless you're willing to accept that certain infinite processes are legitimate, that you have a theory of infinite processes that will actually terminate. So in the 19th century, they didn't have computers. Right? They didn't think so clearly about computational issues. And so this idea of infinite processes, well, for a long time, they didn't really worry too much about it. They sort of just assume that there was a theory of real numbers and there was a corresponding theory of complex numbers, and so that this kind of thing which approximately made sense also made sense exactly if you were willing to sort of assume certain things. But these days, we are increasingly connected to our computers. And this kind of discrepancy between what we can do computationally and what we're claiming to do theoretically is, I think, growing increasingly obvious. And so I think there's actually going to be new ways of thinking about this subject. So the history is not finished. In particular, let me show you another way of approaching the arithmetic here. So suppose you were interested in doing arithmetic with rational numbers and this C. You wanted to include C in your world and do it sort of in a consistent way to have a ring. Well, how could you, for example, prove that if C satisfied this equation, that C squared also satisfied this equation? So here's a question. If f of C equals 0, why is f of C squared also equal to 0? Geometrically, if you have this picture in mind, the answer is sort of obvious, because you could say, well, if this is a 15th root of unity, it means that if you take this angle and you go around 15 times, you get back to there. And that's going to be true then of this one here, which is twice the angle. So if you multiply that by 15, you're also going to get back to there. So if you have this angular picture in your mind, then this is kind of obvious. But it's a completely different story to ask, well, how algebraically does it follow that if C satisfies this equation, that C squared also satisfies this equation? And the answer is, you can compute. If you plug C squared into there, you're going to get x to the 16 minus x to the 14 and so on, all the way down to 1. And then it turns out that that factors, or it can be rewritten as f of x plus f of x times x to the 8 plus x to the 7 minus x to the 5 minus x to the 4 minus x cubed plus x plus 1. This is a different factor from f of x, although it looks quite similar. So this is an algebraic identity that I should probably put, let me put f of x squared here just to make it a correct identity. So this identity shows that if f of x equals 0, then f of x squared also equals 0, because f of x squared is divisible by f of x. All right, so that's x squared. So there must be a similar identity for x to the 4th and a similar identity for x to the 7th and so on. In fact, we can do all of them at once by making the following observation. That if we take x minus y times x minus y squared times x minus y to the 4th times x minus y to the 7 times x minus y to the 8 times x minus y to the 11 times x minus y to the 13 times x minus y to the 14. And now x and y are just free variables. It's just an identity involving high school algebra. That if we expand this thing out, we can write it as f of x, where f is exactly that polynomial, the same one, minus f of y times some third polynomial p of xy. This is somewhat interesting, maybe even remarkable identity. Okay, this is purely an identity in algebra. And that tells us that if x equals y to the, say, 4, if I replace x equals y to the 4th in the left-hand side, I'm obviously going to get 0 because x minus y to the 4th is a term there. And then on the right-hand side, I'm going to get f of y to the 4th minus f of y times p of xy. And so if And that'll tell us that if y satisfies f of y equals 0, then f of y to the fourth equals 0. Because if this is 0, then that has to be 0. And that's true not just for y to the fourth, but also for y to the seventh, y to the eighth, and so on. So this identity covers all these cases all at once. It's interesting because this polynomial, I got Maple to calculate it for me and had a look at it. It actually turns out to be of degree 52. It's a big polynomial in x and y, reasonably big. And the number of terms, I didn't count them, but they were more than 100. There were more than 100 terms. So without a computer, it would be a little bit challenging to study this kind of situation. All right, so what I'm saying here is that although the 19th century mathematicians thought in terms of the complex numbers, it's possible to rethink this story. So even if you're interested in, say, the zeros of this cyclotomic polynomial, you don't have to think about them in terms of complex numbers. You can think of them just as algebraic numbers that are variables that satisfy this relation, and that other relations that you need can be derived algebraically. So there's an alternate scenario that's possible to describe this algebraic number theory business, which was firmly rooted historically in the complex numbers, but which I believe will be rewritten in the coming century, maybe, in something that's more algebraic and more ultimately computational. And we learn something when we do this, right? There's some content here that somehow is invisible when we're operating at this approximate geometrical level. Okay, so but now having said that, so these qualifications, let's have a look at what the 19th century mathematicians did in their language, mostly. All right, so here's the definition of Dedekind that introduces the objects that these people were studying. So he clarified that an algebraic integer is a root of an equation x to the n plus a1 x to the n minus 1 plus a2 x to the n minus 2, and so on, plus an minus 1 x plus an equals 0, where the coefficients a1, a2, up to an all belong to the integers. In other words, to z. And note importantly that the equation is monic. And that means, i.e., that the coefficient of the highest power is 1. All right, that's a monic polynomial. All right, so if you believe in the fundamental theorem of algebra, all right, then this is a reasonable definition because you know that there are n zeros to such an equation, and so there are n complex numbers in the complex plane, and those are the algebraic integers. However, if you're like me, that doesn't believe in the complex numbers in that context, then this is a problematic definition. Okay. So earlier, Eisenstein, who was a brilliant young fellow who passed away prematurely, he was a student of Gauss, I believe. He had shown basically that algebraic integers form a commutative ring. In other words, i.e., that the sum, the difference, and the product of two algebraic integers was another algebraic integer. That's not entirely obvious. Okay? Not entirely obvious. If you have two complex numbers which are the zeros of a polynomial with integer coefficients, that the sum or that the product is also having that property. Gauss had also contributed in this direction earlier, and Gauss had made the observation that an algebraic integer which is a rational number is actually an integer. So let's see why that's true. So for example, if x happened to be, say, r over p times q, where p is a prime, suppose that you had an algebraic integer of that kind, which actually had a denominator, and p was one of the prime factors of the denominator. Then if you plug it in to the equation, then you would get r to the n, and you take the first one to one side, you get r to the n equals minus a1 r to the n minus 1 times pq. And then lots of terms like this, minus an pq to the n. Basically just clear fractions. And bring r to the n on one side, then you would see that, therefore, p divides r. Because p divides all of these terms on the right-hand side, and so it has to divide r to the n, and since p is a prime, it'll therefore divide r. And that's a contradiction, and therefore x has to actually be an integer. Okay, so you might think that there should be then a ring called the ring of algebraic integers. Well, it's kind of symptomatic of the logical problems here that that ring is very inaccessible. It's very hard to say anything about the ring of all algebraic integers. This ring of all algebraic integers, even though it would seem to be a reasonable object of study, is rarely ever studied, I think it's safe to say, and usually is, say, too complicated, we might say. And usually what happens is that we only study small subrings, usually smaller subrings are studied. In fact, it turns out that even very small subrings are quite challenging to understand. So let's have a look at the simplest example. So the simplest example is that of the Gaussian integers. These are like the integers in the complex plane. So sometimes they're denoted zi, or maybe in our notation we would write int I. And they are just things of the form a plus bi, where a and b are integers. In other words, belong to z. So we're just talking about the complex plane, but with all coordinates required to be integers. So we're talking about some lattice, really. A regularly spaced lattice of points in the plane, including, of course, negative values as well. these are algebraic integers. For example, this one here is 1 plus I. That's a Gaussian integer. Or here is 2 plus I. Here is 3 plus 2I, etc. Okay, it's an interesting exercise to show that these are all algebraic integers. They're actually the zeros of polynomials of degree 2 with integer coefficients which are monic. So these are algebraic integers in the definition of Dedekind. And their study is intimately connected with important definition that q of a plus bi is a squared plus b squared, which we might also write as alpha times alpha bar. This is also sometimes called the norm of alpha, but I prefer to think about it as being called the quadrants. Of alpha for two reasons. First of all, this is really an ancient Greek idea, just sum of squares. And secondly, the norm is not such a good terminology. I don't need this concept named after me, for example. But a better reason is that the norm in other places in mathematics and analysis means something different, means the square root of this thing. All right? So it's very confusing to have the same terminology for a concept and its square root floating around in different areas of mathematics. So I strongly encourage us to think about the quadrants, and we'll use the symbol q to denote that number. And the basic property of the quadrants is that the quadrants of the product is the product of the quadrants. Basic property of complex numbers just happening to apply to these special complex numbers of the Gaussian integers. And if we look to see when is the quadrants equal to 1, well, then there are four solutions: 1, minus 1, I, and minus I, and these are the units in this ring. All right, so this is a lot like the integers. Natural question is, are there analogs of primes in this context? What would a prime Gaussian integer be? Well, we can make the definition. We'll say that alpha is a Gaussian prime. Well, if, let's say its quadrants is bigger than 1, so it's not actually a unit, and alpha is not the product of Gaussian integers of smaller quadrants. So what do Gaussian primes look like? Well, interestingly, this goes back to a theorem of Fermat. Important theorem about sums of squares, which is that a prime p is a sum of squares precisely when p is congruent to 1 mod 4. Maybe we should say an odd prime, because 2 is a prime which is a sum of squares also. So an odd prime p is a sum of squares precisely when it's congruent to 1 mod 4. So for example, 5 is a prime which is congruent to 1 mod 4, and it can be written as a sum of two squares, namely 1 squared plus 2 squared. 13 is congruent to 1 mod 4. It's 1 more than a multiple of 4. It can be written as a sum of squares, 3 squared plus 2 squared. But 7 cannot be written as a squared plus b squared. 11 cannot be written as a squared plus b squared. So Fermat stated this. This was actually proven by Euler. Proven by Euler in 1749. So an interesting consequence of this is that that 5 is not a Gaussian prime. Why? Because we can write 5 as, we can factor 5 in the world of Gaussian primes. How? Well, essentially using the sums of squares. So if we write 1 plus 2i times 1 minus 2i, we recognize that we're talking about the quadrants of 1 plus 2i. That's 1 squared plus 2 squared. And so this is a decomposition of 5 into a product of numbers, each of whose quadrants is less than the quadrants of 5. The quadrants of 5 is 25. The quadrants of these two are only 5. Are these primes? Yes, these in fact are primes. So the question of what is a prime has a kind of a different answer in this ring of algebraic integers than it does in the ordinary integers. Something like 7 is a prime. But there are other primes, like 1 plus I is a prime. 2 plus I is a prime. The natural question is, does the fundamental theorem of arithmetic hold in such a domain? Is it true that every number is a product of primes in essentially one way? Okay, we might take a break and then we'll come back and answer that. Carry on.